Space is vast. It's filled with stars, planets, and galaxies. But it also holds mysteries, objects that challenge our understanding of the universe. One such enigma is the black hole, a region in space-time where gravity is so strong that nothing, not even light, can escape its pull. Imagine a place where the fabric of space and time is warped beyond recognition, a cosmic abyss that swallows everything in its path. That's a black hole. Black holes are not empty spaces, but collapsed remnants of massive stars. They are incredibly dense, packing an enormous amount of mass into an incredibly small volume. This density creates an intense gravitational pull, a force so strong that it warps the fabric of space-time around it, creating an inescapable gravitational well. The boundary of a black hole is called the event horizon. Cross this point of no return and you're doomed to be pulled in, stretched and squeezed by the immense gravity. A process scientists call spaghettification. It's a one-way trip to oblivion, a journey from which there is no escape. The concept of a black hole might seem like science fiction, a figment of our imagination, but their existence is supported by a wealth of scientific evidence, from the observation of stars orbiting invisible companions to the detection of gravitational waves, ripples in space-time caused by the collision of these cosmic behemoths. How do these cosmic monsters come to be? The life story of a black hole begins with the death of a star. Stars are giant balls of hot gas, powered by nuclear fusion at their core, where hydrogen atoms fuse to form helium, releasing enormous amounts of energy. This energy outward pressure from the star's core counteracts the inward pull of its own gravity, creating a delicate balance that keeps the star stable for billions of years. However, this balance cannot last forever. As a star ages, it eventually exhausts its nuclear fuel. Without the outward pressure from fusion, the star's core begins to collapse under its own gravity. For smaller stars, this collapse leads to the formation of white dwarfs or neutron stars. But for the most massive stars at least 20 times the mass of our Sun, the core collapse is catastrophic, resulting in a supernova explosion, one of the most violent events in the universe. During a supernova, the star's outer layers are blasted into space, while its core continues to collapse. If the core's mass is sufficiently high, gravity overpowers all other forces, compressing the core further and further until it collapses into an infinitely small point called a singularity. This singularity, shrouded by an event horizon, is what we know as a black hole. Black holes are not just cosmic vacuum cleaners, they are fascinating objects with intriguing properties. For instance, black holes come in different sizes. Stellar mass black holes, formed from the collapse of massive stars, are a few times the mass of our Sun. Supermassive black holes, on the other hand, lurk at the centers of galaxies, including our own Milky Way, and can be millions or even billions of times more massive than our Sun. One of the most exciting discoveries in recent years was the first ever image of a black hole's shadow, captured in 2019 by the Event Horizon Telescope, a global network of radio telescopes. This groundbreaking image provided direct visual evidence for the existence of black holes and confirmed many of our theoretical predictions about their nature. Another intriguing aspect of black holes is their relationship with time. According to Einstein's theory of general relativity, time slows down in strong gravitational fields. This means that time would tick slower near the event horizon of a black hole compared to a distant observer. It's a mind-bending concept, but it's a consequence of the warping of space-time by massive objects. Black holes can be difficult to grasp, but let's use a simple analogy. Imagine a bowling ball placed on a trampoline. The bowling ball represents a massive object like a star, and the trampoline represents the fabric of space-time. The bowling ball's weight causes the trampoline to sag, creating a dip around it. This dip represents the warping of space-time caused by the star's gravity. Now imagine rolling a marble across the trampoline. If the marble is rolled with enough speed and at the right angle, it will orbit the bowling ball, just like planets orbit stars. However, if the marble is rolled too close to the bowling ball, it will fall into the dip, unable to escape. This is similar to how black holes work. The bowling ball's dip represents the black hole's gravitational well, and the marble represents anything that gets too close to it, including light. Once something crosses the event horizon, the point of no return, it's trapped forever within the black hole's gravitational grasp.